This is our second presentation for our Sea Otter Science Symposium, our fourth year. And I'm going to pass it off to Bob Bailey, who is our board president for the Elakha Alliance, to open up our next presenter.
Thank you, Chanel, and thank you everyone for attending our fourth annual Sea Otter Science Symposium. You'll notice that there aren't many sea otters on the agenda today, but it's all about sea otters ultimately. Our next speaker is going to take us from the global down to the local and talk about changes to rocky reef habitats on the southern Oregon coast. Dr. Steve Rumrill is going to present that to us. I've known Steve for many years and admired his work. He received his master's degrees in marine science from the University of California at Santa Cruz and his Ph.D. in zoology from the University of Alberta. He is currently the Shellfish program leader for the Oregon Department of Fish and Wildlife, with statewide responsibilities for management of a multifaceted program that encompasses policy development, resource assessment surveys, commercial and recreational fisheries, scientific research, and outreach activities for a diverse group of shellfish that inhabit Oregon's bays, estuaries, sandy beaches, and more. Before joining the Oregon Department of Fish and Wildlife, Steve was the chief scientist and research coordinator for the South Slough National Estuarine Research Reserve in Charleston. And Chanel can put up some links to Steve and some of his work in the chat box for you. It's my honor and pleasure to introduce Steve, who himself is a musician, and to bring him on board to tell us about changes to rocky reef habitats on the southern Oregon coast. Thank you, Steve. It's all yours. And I'll let you share screen.
All right. Looks like I can't turn on my video. Can you flip my video on there too, Chanel?
Yeah, hold on one second. Sorry. Let's see here.
While you're looking for that, I'll just get started. So first of all, I want to just thank the Elakha Alliance, Bob and Chanel in particular, for this opportunity. I really enjoyed the invitation and the work to pull this information together. I'm going to provide you with a whirlwind overview, as Bob said, kind of bringing things back to earth after that wonderful first presentation. I'm going to provide a whirlwind overview of several relevant issues, more local or regional issues, and factors that are relevant to consideration of the reintroduction of sea otters to the Oregon coast. This is a complex topic that really is worthy of substantial investigations. So I'm going to really just describe more of the nuts and bolts kind of approach, or a boots on the ground approach to thinking about some of the habitat issues, some of the shellfish fishery, prey resource, trophic cascade issues, and really I'll just do this in a quick manner. So I'm going to talk about changes to, as Bob mentioned, rocky reef, but also I'm going to also include a little bit of information about estuarine habitats down the south coast. Let's see. So how's this go? Okay, so outline for this talk, I'm going to start with a quick preamble and just describe a quick summary of the ODFW shellfish program. Then I'm going to move into talking about baseline characterizations of habitats before the reintroduction of sea otters, my own personal experience there. I'm going to provide a recap about rocky reef and estuarine habitats as potential locations for the reintroduction of sea otters. And then I'm going to spend the bulk of the talk talking about a situational update, describing the recent shifts in rocky reef habitats and management of our prey shellfish prey resources along the south coast, and also talk about characterization and shifts in estuarine habitats in Cruz Bay. I'm going to finish off by chatting briefly about a new project jointly between ODFW and U.S. Fish and Wildlife Service called CSWIG, or Competitive State Wildlife Grant, that focuses on species of greatest conservation need down in the South Coast. And then I'll finish off by acknowledging the complexity of these trophic cascades and open it up for questions. So overview of the shellfish program. Shellfish really are defined as marine invertebrates with an exoskeleton that are harvested commercially or recreationally for food. We have we place a great ecosystem value on the harvest of shellfish, and sea otters do as well. They're primary food items for sea otters. The ODFW Shellfish Program has a mission. Our mission statement is to assess, monitor, and manage shellfish resources, marine invertebrate communities, and their habitats to provide sustained ecological, commercial, social, and recreational benefits for current and future generations of Oregonians. As a director of the Shellfish Program, I've divided it up into 5 different sections: conservation, monitoring, and management. Second, infrastructure and accountability. Third, our stock assessment and habitats. Fourth, shellfish science. And fifth, our outreach and education. We manage in this program commercial fisheries and recreational fisheries, targeting on the priority shellfish: crab, bay clams, razor clams, pink shrimp, abalone, urchins. And we work in cooperation with the Oregon Fish and Wildlife Commission and Oregon State Police on revising, updating, creating new statutes, policies, regulations, rules, and management actions to help guide the management of shellfish, and then also the state police dealing with enforcement and violations. We have a great diversity of shellfish in Oregon, a large list of commercial fisheries, including well-known Dungeness crab, red rock crab, tanner crab, pink shrimp, bait shrimp, bay clams, razor clams, scallops, sea urchins, etc. And that combined value of about 20 different species, about 80 to 100 million a year. On the recreational side, an even greater diversity, almost the same list, but even more. And a little less, about 60 to 80 million dollars or so annually in indirect costs. Now, my personal journey in terms of working with the reintroduction of sea otters, I've been involved in baseline characterization before sea otters are introduced into habitats twice in my past, and now thinking about this for Oregon is the third time. First time was down at San Nicolas Island, located offshore from Southern California. And that was baseline characterization of the intertidal and subtidal habitats scattered over many years, 1976 to about 1990. That work, so I lived and worked out on the island briefly for periods in the summer as a scuba diving intertidal technician and worked all around the shoreline of this island. That work resulted in the reintroduction of about 140 sea otters in 1990, and followed very rapidly by a decline in those translocated otters. But then over the past years, a slow increase to current about 150 otters in 2020. The second was up in, that baseline characterization down at San Nicolas Island, headed up by U.S. Fish and Wildlife Service, Santa Cruz guide Jim Estes, and my major advisor, John Pierce, and a whole series of diver technician graduate students. And it was really where I cut my teeth working with the intertidal marine organisms, subtidal scuba diving at that site. It was really a wonderful introduction to the marine sciences when I was just beginning to learn about this. Second characterization was when I moved up into Canada, into British Columbia. I conducted my own Ph.D. research at the Banfield Marine Station, which is in a wonderful habitat located along the shoreline of Vancouver Island in Barkley Sound. And as a part of that thesis, I was working to help characterize the subtidal communities in anticipation of sea otters coming down. Working in collaboration with Jane Watson at that site. Sea otters were introduced into the habitats in Vancouver Island over that period from 1969 to 72, but they were absent from Barkley Sound until after the period I was gone, well after I was gone. up until about 2010. So here we are now thinking about baseline characterization before reintroduction of sea otters to the Oregon coast. And the southern Oregon coast includes diverse marine and estuarine habitats that have the potential to support otters. Those include capes and headlands and coves, nearshore rocks and islands, rocky shores and sub-tidal reefs, kelp beds, the estuarine habitats, eelgrass beds, and substantial shellfish prey resources. Key ecosystem attributes required by sea otters. Sea otters really just need protected habitats and adequate prey resources. Otters typically inhabit semi-protected areas, including shallow rocky shores, kelp beds, and eelgrass habitats. We all know that they eat a whole lot, 30% of their body weight per day. They consume a wide diversity of prey items, including urchins, sea stars, crabs, mussels, abalone, clams, snails, lots of different invertebrates. Sea otters can exhibit individual foraging specialization, and they can switch from one group of prey items to another. And of course, they exert top-down control over the communities. Their predation activities influence the food web links and these trophic cascades. So the shifts in their abundance of prey species end up modifying the structure of the marine and estuarine habitats. Therefore, we characterize them as keystone species. Now we began to think about this issue associated with introduction of a keystone species that has the potential to modify our ecological communities into the southern Oregon coast. We have to also place this into the context of the now. And the situation down along the Oregon coast, southern Oregon coast, is dire, unprecedented in recorded history. A series of events that we're just characterizing at this point, but it's super important for us to just think about the local context. So I'm going to describe a series of events beginning with the marine heat wave of 2014 to 2017, extending into 2020, the increased abundance of purple urchins and formation of urchin barrens at some of our sites, sea star mortality associated with sea star wasting disease, the decline of red abalone, and the patchy demise of bull kelp along our coast. Collectively, they form up a series of events that has put a lot of stress on our South Coast communities at this time. So really, the perfect storm occurred. A non-normal events prompted management action, beginning with elevated seawater temperatures known as the blob or marine heat wave, 2013 to 2015, developing and then extending up into the present time. The warm seawater was associated also with a concurrent sea star wasting disease that killed off literally billions of sea stars, 2013 to 2015, extending into the present, coupled up with massive recruitment of purple sea urchins, 2013 to 2015, followed by growth and increased foraging by those adults, 2015 to the present, and also coupled up with a decline of bull kelp in key areas, 2015 to 2017, persisting into the present. All of these events contributed to the decline of red abalone in Northern California and Oregon, and prompted the Oregon Fish and Wildlife Action to suspend the recreational abalone fishery from 2018 to the present. They long ago prohibited commercial take of abalone in Oregon. So these changing situations present a pressing ecological situation and a complicated management problem as we consider introduction of sea otters into this stressed series of habitats. Again, just some flow diagram that links the marine heat wave with sea star wasting, recruitment of urchins, decline of kelp, and decline of red abalone. So the marine heat wave, just a quick picture there. Observations back in 2014, Pacific Ocean waters experienced substantially warmer temperatures and this huge blob of warm seawater offshore, sweeping down from Alaska through British Columbia, all along the west coast, down into Mexico. This is the greatest heat wave recorded since 1981. And it persisted for many years, 5 or 6 years, till it finally began to break up in 2020-21. Still exists offshore, but this graph on the right shows some of that colder water upwelling along the coast of Washington, Oregon, and California. As you know, we fluctuate naturally between cool and warm ocean waters, and this time series just shows that recent fluctuation between cool waters in 2010 to 2014, and then a rapid change into anomalously warm water from 2014 to about 2020, and then back to cooler waters in that La Nina years that we're recently experiencing. Now, the switch between warm and cool phases brings with it changes in the ecological communities, biological communities. Well known to those of us as marine scientists along the Oregon coast are changes in the composition, species composition of copepods as an indicator of cold water with larger, nutrient-rich, lipid-filled copepods during the warm water or cold water years, and a whole different group of copepods associated with warmer water. And they provide less nutrients to our nutrition to the krill and salmon that are out in the water column. NOAA Integrated Ecosystem Assessment Program operates the California Current Marine Heatwave Tracker, or the BLOB tracker, and the observations currently are that we're seeing a reemergence of a secondary heat wave during the late summer of 2022. This is the fourth largest marine heat wave in this region since about 1981, 82. And the warm water is located mostly offshore for most of August and encompassed most of the coastline from Alaska down to California. But small patches of cool water are remaining in locations along the coast due to local upwelling. So if you look at this graphic, you can see these cooler waters right along the coast, but warmer waters further offshore. Marine heat waves are widely recognized for their capacity to disrupt marine ecosystems. And the reported impacts include alterations of primary productivity, proliferation of harmful algal blooms, displacement of ocean habitats, changes to the disruption of distribution and populations of marine species, disruption of commercial and recreational fisheries, and increased conflict between humans and wildlife. And when we think about this, what does this mean on the ground to the Oregon coast? The marine heat wave of 2014 had a big impact on our coastline. One of the habitat attributes, of course, that felt that impact is bull kelp. And, just thinking about the ecology of bull kelp in Oregon waters, it's a key habitat that supports complex marine communities. Bull kelp is typically found on rocky areas, rocky substrata exposed to waves, can extend from the surface down to depths of about 40 meters, considered as an annual species, but the canopy forming blades can persist up to about 18 months. And out on those blades are the formation of spores and sori. These are where the reproductive viable propagules are produced. The spore patches grow quickly, release spores that settle back down onto the bottom and begin to grow up. And they're particularly vulnerable to grazing by not only urchins, but by snails and other critters that are grazing along the bottom. Bull kelp decline occurred along our coast and down in Northern California, well documented in Northern California. Excuse me. Here, a nice paper by Laura Rogers Bennett showed the before and after situation shown on the photographs on the left with the demise of kelp after 2015 and the conversion of rich understory kelp and understory seaweed areas into urchin barrens. That was coupled with, on the right, the decline in populations of the sunflower sea star, a big soft-bodied predatory sea star, declined in abundance over time due to sea star wasting disease. And that was coupled with the steady increase in the abundance of purple sea urchins, which then graze the understory seaweed and remove kelp. Kelp was not recovering in parts of Northern California as of 2019-2020. The hypothesis, working hypothesis, was that loss of sunflower stars from seawater, from sea star wasting disease was coupled with the increase in urchins because they were released from predation. What about the Oregon coast? So great work by Sarah Hamilton when she was a graduate student at Oregon State University, took a look at the history of kelp here. And bull kelp beds are naturally variable in space and time along the Oregon coast. And like Northern California, she documented that bull kelp was reduced at some sites after the marine heat wave, Orford Reef and Humbug Mountain, but bull kelp increased at other sites like the Rogue Reef or Redfish Rocks and Cape Arago, and were static at other areas like Depot Bay. We also know from her work that bull kelp is variable annually, seasonally, and spatially. So this time series at the top shows greater variability in bull kelp spatial coverage before the urchin fishery. The urchin fishery in Oregon began really in the late 80s, and then the bull kelp variability declined, but was still variable year to year, season to season. And the graph down below just shows most of the bull kelp is located down in the south part of the state. So when we think about bull kelp and the importance of kelp to these other communities, urchins, sea stars, abalone, it's vital that we have healthy kelp beds. Now, here, my team has been looking at the community of underwater kelp and marine invertebrates for many years. And what I'm showing you now are some side-by-side video, underwater video, taken in 2011, and the same exact transect lines taken in 2019. And what you're seeing is really a shift in the underwater communities. Back in 2011, we considered that as normal habitat, but in 2019, you'll see the conversion underwater of that rich habitat converted into an urchin barren. The rich habitats are characterized by high biodiversity of seaweeds, kelp, and invertebrates, lots of algal biomass, several sea stars in this video, and few sea urchins. In the conversion to the more recent characterization of these habitats in 2019, is characterized by low biodiversity of algae and seaweeds and marine invertebrates, very little algal biomass, few sea stars, and lots of sea urchins. So what we've really seen is a conversion of these rich habitats on the left to more, less rich, less biodiverse habitats on the right. Okay, so let's focus now a bit more on sea star wasting disease. So sea star wasting disease really hit many species of sea stars all along the West Coast. And in particular, we noticed, the death and demise of the ochre star, this purple and orange sea star. Ochre stars are also very important predators that are considered as keystone predators that control the species composition and abundance of a large number of organisms in the intertidal zone and shallow subtidal zone. And the onset of sea star wasting disease for ochre stars was coincident with the marine heat wave. It was first observed in California and Washington in 2013, followed quickly by Oregon in 2014, spread from Alaska down to Baja California, and affected over 20 species of stars. I won't go into the possible causes there, but it's considered as the largest marine disease event ever in recorded history, possibly caused by a virus or perhaps localized hypoxia at the level of the sea star epidermis. And we still see remnants of sea star wasting syndrome along our coast. Here in Oregon, Bruce Mengi and his group carefully documented the demise of Ochre stars at many locations along the Oregon coast. They documented 60 to 90% declines of Pisaster throughout Oregon's intertidal habitats over that period from 2014 or throughout 2014. Now, what about down in the subtidal zone? So sunflower stars, Pycnopodia, were also severely affected by sea star wasting disease. And this series of photographs shows the same rock in Vancouver Island over a period of 3 weeks. Massive numbers of sea stars, and then 3 weeks later, all gone. And they didn't just walk away. You can see the white in this photograph as the ossicles from those stars that died in place and fell to the bottom. The massive mortality of sunflower stars along the West Coast has been documented for Washington, Oregon, and California. And throughout the area, about 100% decline in California and about 99% decline in Washington, and none observed in about 700 trawls along the coast. So some very serious decline in sunflower stars along the West Coast. Here in Oregon, so we are concerned about coastwide decline, and that 90% coastwide decline throughout their range from Alaska to Baja. That prompted the International Union for Conservation of Nature to list them as critically endangered in 2019, and they're under consideration for a decision at the federal level pending later this year. So we saw about a 98% decline along the Oregon coast. I want to note, though, that that massive decline really between 2014 and 2015, but also we saw perhaps some earlier signs in a steady decline from 2011 down to 2013, 2014, 2015, a multi-year decline before sea star wasting disease was officially recognized. So we had a problem, and the Oregon Fish and Wildlife Commission took action to prohibit recreational take of all sea stars. And so we're happy that they took that action, recognizing this as an important conservation action at this time. Now, when we think about variability in abundance of echinoderms along the Oregon coast, not all species of echinoderms responded to these stressors, marine heat wave, and the multi-stressors associated with marine heat wave and sea star wasting the same. There's a group of species that exhibited decreased abundance, like the sunflower sea star Pycnopodia, shown here on the far left, but that was also shown by the giant pink star Pisaster brevispinus, very similar pattern, and multiple species of Solaster stars, Solaster stimpsoni, Solaster dawsoni, perhaps other solasters as well. Other species like Pisaster ocratius showed a dramatic decrease immediately between those time periods of 2013 to 2015, but then have shown some recovery. And we've seen that as well in Henricia, the blood star, a dramatic decrease followed by some recovery, such that now we're almost not quite fully recovered, but no overall change on the scale of decades. And then other species showed increased abundance. Of course, the red urchins increasing and purple urchins increasing, but also some stars like the leather star, Dermasterius imbricata, increasing following that immediate loss due to sea star wasting. So some curious patterns here among the different types of echinoderms. The recent changes along the rocky reef habitat, as we've described it, moving into this urchin barren on the right, has been attributed in part to the decline in sunflower sea stars. So sunflower stars prey upon a variety of invertebrates, including barnacles, hermit crabs, clams, snails, sea urchins, sea cucumbers, and sand dollars. And without the sunflower stars, then the purple urchins devour kelp and seaweed and create these urchin barrens. So that's really the working hypothesis for top-down control. But is there really empirical evidence to support it? It's difficult because we have to do a post facto assessment. Now we know from work up in Barkley Sound, some of my work and others up there, that sunflower stars prey upon this diverse variety of prey items, but only about 4 to 5% of the stars during our surveys consumed sea urchins. So it poses a question, if sunflower stars are really controlling the abundance of urchins in the sub-tidal, they may be preying, upon a higher abundance down here in Oregon than they were in British Columbia. Something's up. It just doesn't quite feel 100% correct that this is a direct trophic cascade top-down control. Our new video counts of echinoderms along these subtidal habitats show that the decline of sunflower stars occurred here in Oregon about 4 to 5 years before the dramatic increase in purple and red urchins. Up at the top, the purple arrow down shows that decline time period from 2010 to 2013, and really a dramatic decrease in 2011 to 2012. But there was a long delay in terms of when we actually saw the dramatic increase in red urchins, not till 2015 to 2016. And those urchins needed a time period to grow, and speculation that they settled out of the water column and entered the benthic phase of their life, perhaps as far back as 2011 to 2012, concurrent with the decline in sunflower stars. Purple urchins, another lag, didn't really increase in abundance till between 2015 and 2016, and they grow faster, but that indicates they may have had a settlement event in 2014. So there's a significant lag between the decline in sunflower stars 2011, 2012, and increase in recruitment when we notice the red urchins and purple urchins coming into the populations in 2015 and 2016. So this gives us a bit of pause and prompts the question, to what extent did the demise of sunflower stars actually contribute to the increase in urchins and loss of kelp? Our new video findings show that significant 4 to 5 year delay between the demise of sunflower stars and the increase in purple urchins. So an alternate hypothesis may be that the demise of sunflower stars is associated with ecological factors that contribute to reproduction, survival of post-larvae, newly recruited urchins, or adults. A more complex hypothesis that takes into account the situation that's been proposed before, but opens up the thinking to perhaps some more bottom-up control or factors that may have contributed at a much more cryptic ecological level, thinking about post-larvae and very small juveniles and their impacts in the subtidal system. Okay, let's shift over and talk quickly about some of the shellfish prey down along the south coast. I'm calling them shellfish prey because they're prey for humans. These are targets for our commercial fisheries, in some cases, recreational in others. And yet at the same time, we recognize that they would be likely prey items in the event that we had an introduction of sea otters. So first, I'll start with Oregon's commercial sea urchin fishery, focuses on red urchins and purple urchins. Sea urchins have long lifespans and notoriously episodic recruitment. They can go for many years, sometimes a decade or two, without significant input of small juveniles into the populations. They occupy subtidal habitats, rocky subtidal habitats along the south coast. This is a dive fishery with a long-term annual harvest level of about 500,000 pounds per year. The landed value, economic value, has varied over the past 30 years or so from about $2 a pound to a high now at about $15 a pound. So that computes up to an ex-vessel value to the harvesters, ranging from $2 million to $7 million a year for the total fishery. And the fishery product, of course, is uni, the urchin gonads shown in the photographs down on the bottom. Commercial landings along the West Coast have occurred from the 70s up to the present. In the early years, the first 20 years or 15 years or so of the fishery was all focused down in California. And then and when that fishery began to show signs of depletion, California fisheries then shifted up, and the harvesters moved up into Oregon. And then we had a combination of California and Oregon. And Oregon peaked up in about 1990, 89, 90. And then since that time, the take in California has been the greatest along the West Coast. And then it stabilized, moved down to a much lower, what we think as a sustainable level over the past 20 years. I want to note that the lowest catch for the whole West Coast occurred immediately before this massive recruitment event. So most of the commercial harvest here in Oregon occurs down along the South Coast, about 50% off of Orford Reef, about 25% off Rogue Reef. These are offshore reefs, series of islands offshore from the South Coast, and also near shore up in Depot Bay, about 9 to 10%. The figures down below show that each black dot records a location for a diver's harvest. And we keep tabs on that, and the divers search and harvest throughout the kelp areas. So they're exploring and harvesting. When they hit good patches, they'll work there. But their harvest activities are really centered along the inside throughout our bull kelp. The histogram here just shows the history of catch and permits. So in the 30 years that I've been affiliated with Shellfish here in Oregon, we have moved from a peak harvest of sea urchins along the South Coast, 1988, where we allowed 98 permits, almost 100 permits. It was a very lucrative and very active fishery. And I was concerned about it, though, becoming over-harvested and too many people recognizing that the wild virgin harvest that had not been harvested by humans for 100 years was not going to sustain. And so working with the urchin harvesters, we reduced that down to 46 permits in 1989, and then further reduced that in 1995 down to 30 active permits. And in 2014, reduced that again down to where we are now with 15 active permits. So when we look at what has occurred there, then we plot that all up as a dynamic response pattern for the commercial catch of red urchins. That period of 1988 to 1990 was really the ramp up of the fishery. It reached its peak harvest in 1990, and then in the period of 1991 to 95, exhibited a downsizing of a diminishing fishery as the wild easy pickings harvest became less and less available. And then we entered into this period where we are now, 1996 to the present, stabilization of what we believe is a sustainable fishery. So there's been wide variability in the biomass and harvest activity of urchins over the past 30 years. Now, there's also wide variability in market demand and variability in the ex-vessel value of urchins harvested from Oregon. Again, the fishery value is as uni, and that's varied from about $4.50 a pound, or generating about 2.3 million ex-vessel values back in early 90s, dropping to about $2.75 a pound, dropping it down to about 1.5 million ex-vessel about 2005, and then shooting up to $15 a pound now, and increasing the ex-vessel value of the total fishery to $7.5 million. So we also need to recognize, though, of course, that the gravid urchins are the valuable urchins, but empty urchins or zombies do not have retail value. So gravid urchins are healthy. They have plenty of algal food. They generate gonads, which is high-grade uni, and they are given a high economic value on the retail market. In contrast, the huge numbers of urchins in the urchin barrens are starving. They're poorly fed, and the poor nutrition means no gonad, no uni, and they have little economic value on the retail market. There are efforts underway to ranch and feed these urchins in captivity. and that you can produce that with that human intervention, but it's costly in order to create uni in starved urchins in a ranching situation. Okay, ODFW has been conducting population surveys at index sites for many years, up in the North Coast, centered around Depot Bay, South Coast in the area from Cape Arago and Gregory Point, and down around the South Coast at Orford Reef, Redfish Rocks, and Humbug Mountain. Our index surveys are belt transects, where we place divers underwater and they swim along transects 30, 40 meters and record everything that they find on a meter on either side. And we do these at multiple locations along the coastline. What these index surveys show us, they reveal the underlying structure of the population. And so the graph on the right just shows the size distribution of red urchins from our index surveys, shown in the lightly shaded areas, in comparison to information that we get by monitoring the commercial take, by measuring the urchins that are brought to the surface by the commercial divers. So what the population index surveys show us is that we had a massive recruitment event in 2014 to 2015, and that we are speculating by back calculating that that's associated with settlement in 2011 to 2012, followed by rapid growth from about 25 millimeters to 60 millimeters over a period of 2 years or so. So you can see that 2011 settlement, and then that cohort, that bump of small urchins that we guessed were about 2 to 3 years old, growing over that period of 5 to 6 years to that intermediate size, and then scooting over to this period where they are really marketable after a period of 10 to 12 years. The population surveys also showed us, once again, changes in the density over that 30-year period. But I just want to emphasize that the lowest densities occurred immediately before the massive recruitment. It's kind of curious. Okay, and this made the news. So, ABC News, swarms of sea urchins wreak destruction along the West Coast. We were quoted showing that our 2019 survey showed 350 million new purple urchins at Orford Reef. And we were asking the question at that time, is release from predation by sea stars responsible for this dramatic increase in purple urchins? So we also want to think about this question. To what extent can commercial urchin divers function in a manner that's similar to sea urchins or sea otters to reduce densities of urchins, reduce grazing pressure, and help facilitate growth of seaweeds and kelp? One way, of course, is by physically removing these gravid urchins and selling them on the commercial market, but also by the active culling or killing of the zombie urchins. And we're involved in that, and I believe Tom Calvanese will speak about this in a subsequent talk here today. Okay, let's shift focus over and think now quickly about Oregon's other shellfish, abalone. So we have red abalone, flat abalone on our coastline. And we had a commercial fishery very briefly from 1960 to 62. Oregon Fish and Wildlife Commission very quickly recognized that was not sustainable and outlawed that, but allowed a recreational fishery from 1953 up till 2017. And then we recently, in 2018, suspended the recreational fishery while we work on development of a conservation fisheries management plan. Red abalone their biogeographic range extends from Cape Arago down to Baja California. So here in Oregon, that population is at the northernmost limit of its natural biogeographic range. Population density is currently greatest along the northern Oregon coast, and the populations are very low, naturally very low and patchy along the southern Oregon coast. There's a gap in the population surveys between the Oregon-California border and Cape Mendocino. Oregon Department of Fish and Wildlife has conducted our population surveys along the south coast, and the California Department of Fish and Wildlife has conducted their surveys right at the heart of their population in the area around Cape Mendocino and immediately south. But there's a big gap in that area between Mendocino and the North and the California-Oregon border. The sport fishery in Oregon was mostly, well, about 50% scuba and 28%, 30% skin diving, and then about 20% picking along the shoreline in the lower intertidal zone. We issued about 300 sport permits per year, and that take, the sport harvest, was about 189 abalone per year, averaged out over that period from 2007 to 2016. In contrast, California issuing orders of magnitude more, 25,000 permits per year with an annual take of about 239,000 abalone per year, and no scuba allowed. So Oregon is really just a very small sport fishery in comparison to California. So why do people, why are they attracted? Why do they hunt for abalone? For shells, trophy shells. So red abalone are the largest species of abalone in the world. And like many animals, abalone grow to their largest sizes at the northernmost limit of their biogeographic range. So this means that Oregon red abalone are the largest in the world. And indeed, the largest abalone in the world has come from the southern Oregon coast. Now we face some problems. So we have low densities of red abalone in Oregon naturally, and this calamity associated with marine heat wave, loss of kelp, loss of drift algae, competition with large numbers of sea urchins has contributed further to their decline. So from the period from 2015 to the present, we've been conducting underwater surveys to characterize their abundance in these habitats. So they naturally occur at very low densities at the northernmost limit of their range. But the low densities now we see in Oregon are below what we view as critical threshold levels. The graph at the right shows you the perspective, the bell-shaped curve from the perspective of the ocean. I apologize for these not being in sync, but north is to the left. So the small population is at the tail end of the bell-shaped curve up at the north, and the bulk of the population in the middle of California. The histogram at the bottom shows south on the right and north on the left. But as you can see, the population in Oregon, shown way down here in 2015, was below what we consider as a threshold level required for successful reproduction. The Oregon Fish and Wildlife Commission suspended the harvest in 2018, and we are now working to develop a regional red abalone conservation fisheries management plan. So the decline of abalone along the Oregon coast, key factors: low densities result in poor reproductive success. The clustered abalone were easy targets for harvest by sport harvesters when that was allowed, but we could surmise that they would also be easy targets for sea otters in the event that they're out and foraging and looking for food, where they'd be vulnerable to predation by otters if they were there. Normally, red abalone live in cracks and crevices down below boulders and that kind of thing, where they capture drift algae when algae is abundant, and they're beyond the reach of, typically beyond the reach of foraging sea otters. But when food is scarce and they're unhealthy, they're out foraging around. They come out of those protected cryptic habitats where they're very vulnerable to predation. So right now we have very little food for foraging by red abalone. The kelp beds are reduced, and we have increased purple urchins, which are competing with them for food. And we've also got the aftermath of sea star wasting disease, which may be responsible for the absence of urchin predators, and also sea otters are missing from our nearshore rocky habitats. Now, when we think about some other kinds of habitats that can provide habitat for otters, we often think about the estuarine habitats and a well-documented situation down in Central California at Elkhorn Slough. In that case, sea otters are introduced into an estuarine environment that's characterized by eelgrass beds, crab, clams, grazers on eelgrass, epiphytes, a very different kind of situation than the typical kelp bed situation that we consider. But some very nice work down there by Brett Hughes showed that before otters, their situation was that eelgrass cover was very low. But after sea otters were brought into those eelgrass beds in the Elkhorn Slough estuary, the biomass of eelgrass increased. And the thought is, and really well documented, that that trophic cascade was that the predation by otters, they preyed upon crab and decreased the crab biomass, and that resulted in an increase in the biomass of grazers, slugs, and small crustaceans that feed on epiphytic algae growing on eelgrass. And that freed the eelgrass up to grow unimpeded by the epiphyte load. And we had an increase in the biomass of emergent eelgrass. So predation by otters resulted in an increase in eelgrass, a very nice trophic cascade there. Now, if we think about that, would that occur in the Cruz estuary if we introduce sea otters there? Can we expect that foraging by sea otters will have a similar effect in the Cruz estuary? I have to question that because the Cruz estuary is very different in fundamental structure in comparison to Elkhorn Slough. Cruz estuary is a drowned river mouth estuary surrounded by coastal forest watershed. It's very lightly loaded by nutrients and is not showing signs of eutrophication. The eelgrass beds have a very light epiphyte biomass, and we don't believe that the eelgrass in the Cruz estuary is currently restricted by epiphyte loads. In contrast to Elkhorn Slough, the watershed is characterized by intense agriculture for Brussels sprouts and such. Is characterized with heavy nutrient loading and eutrophication. The eelgrass there carries a heavy epiphyte biomass, and the epiphytic growth or epiphytes restrict the growth of eelgrass. Well, what could we expect though? So probably not that same trophic cascade, but we could see some positive ecosystem benefits associated with otters in the Cruz estuary. We could expect predation by otters would result in a decreased biomass of crab and a decrease in the biomass of burrowing clams, and that foraging for crab and clams would result in disturbance to eelgrass. How would this work? Perhaps we can look to the new results up in British Columbia. My old friend Jane Watson and her students there have shown that disturbance to sub-tidal eelgrass by foraging sea otters results in the formation of otter dig pits, and those dig pits increase the genetic diversity of eelgrass. There's a photograph just showing an otter dig pit in a semi-protected habitat in British Columbia after a sea otter has dug for clams. They really can excavate some pretty deep pits. A new paper just come out by this group has really shown that disturbance of the subtidal eelgrass by foraging sea otters increases genetic diversity of the eelgrass bed. Panel on the left, A, no disturbance, the genetically identical plants, eelgrass plants scattered throughout the bed. But panels B and C show that when otters are present and they're digging for clams in there, they disturb the eelgrass bed, and the eelgrass responds by producing flowers and seeds and reproducing sexually and increasing their genetic diversity at the scale of the bed. A very nice alternative trophic cascade and ecosystem response in response to foraging by sea otters.
Getting down towards the end, Steve, here.
All right, I'm going to just get close to wrapping up here. So I just want to make a couple of quick points here. The ODFW SECOR program also works to characterize baseline characterization of estuarine habitats and shellfish communities in bays and estuaries along the Oregon coast, including Coos Bay. So we have a complicated and sophisticated sampling design throughout the intertidal and subtidal zones of the bays and estuaries. We conduct a rapid assessment at many sites to be able to characterize the intertidal areas with field workers out there. And we also do a more detailed extractive sampling, where we dig holes in the mud with gas powered generators and by hand to extract out the bay clams. And just some images there, seeing what that looks like. We also characterize the eelgrass and algae at these sites and generate data that has many uses for the management of shellfish fisheries, to help us understand these habitat associations, provide information for planners and useful and permit review, et cetera. And we generate bay clam maps that are of great value and valued by recreational harvesters. So this baseline information is also, I think, relevant to thinking about the possible introduction of sea otters into the estuarine environment. Our partners down in the South Slough National Estuarine Research Reserve have been monitoring eelgrass in the South Slough estuary for many years. And they've also now shown a dramatic decrease at some of the sites down in the Cruz estuary. Photograph 2002 at Bellino Island shows a beautiful, expansive, very dense eelgrass bed in the intertidal and shallow subtidal at Bellino Island, mid part of the estuary. But 2018 on the right, that eelgrass bed is greatly, greatly diminished, very patchy, if at all. And this graph on the left just shows the demise of eelgrass in the South Slough at the sites throughout the area that they've been monitoring. Most of the areas have shown that decline and predominantly in the tidal inlet area. So it's a major concern about decline of eelgrass there already that would provide some more context for concern about reintroduction or further disturbance to those beds. Finally, I'm going to wrap up by just describing really quickly a new project, the Competitive State Wildlife Grant Program, focusing in on filling critical data gaps to address these recent declines in species of greatest conservation need. Our first objective is to characterize the current status of these species with scuba surveys and ROV underwater surveys in shallow and deep water habitats. Second, to determine the location and spatial extent of rocky reef habitat and kelp beds with high resolution aerial imagery. And then third, to generate new time series data to measure variability in nearshore water parameters. So we're focusing in on the suite of species of greatest conservation need, focusing in on many locations down along the South Coast for scuba dives and underwater ROV work. I won't go into the details of it, but our scuba dives will be conducted by Aaron Galloway and his team down at OIMB. Internally within ODFW, Scott Marion and his team working with the ROVs to characterize habitat conditions in the deeper water habitats beyond diveable depths. And then we just finished, Scott coordinated the new aerial surveys of Oregon kelp beds. So just did that for the North Coast, Central Coast, and South Coast. And so we're looking forward to having those new images. I won't go into the details of it, but we have very high quality, high resolution images taken in October of this year. So we'll be able to characterize the current status. And then finally, we're placing moorings out at locations down there to measure the current condition of seawater temperature, dissolved oxygen, and other parameters. So to wrap this up, conclusions. The marine and estuarine habitat to support sea otters occurs along the southern Oregon coast. Substantial shellfish fisheries exist, which may become prey resources for sea otters. Our team at ODFW is working to characterize shellfish resources and their habitats, and also to monitor the shellfish fisheries. Changing ocean conditions have contributed to substantial shifts in the habitats and communities, and that poses the situational conditions for us to consider reintroduction. Trophic cascades, as we know, are complex, and they warrant additional research prior to introduction of sea otters along the Oregon coast. And predation activities by otters are expected to contribute to ecosystem benefits, both in marine and estuarine habitats. So with that, I just want to leave that final thought. I feel like Columbo here, just making sure that everybody's aware that empirical studies and new research is needed to identify the primary factors and ecological processes that will respond to sea otters in Oregon's rocky reefs and estuarine systems. We kind of know how it's going to work, but we need to really work through the process to make sure we get all the details straight. And then finally, I want to just leave us with some good advice from father of a lot of all this, Dr. Jim Estes, who gave us the advice to don't try to identify a goal that's too far out into the future. Recognize that the world is always changing around us, and the key to success is recognizing the opportunities that arise as the changes occur, and then making wise decisions and selecting where we go based on those opportunities. So with that, I want to thank you for the opportunity to share this whirlwind overview, and Bob for prompting me and giving me the invitation. And with that, I'll just leave it here. So thanks very much.
Wonderful. Thanks, Steve. That was so packed full with thorough information. I am still absorbing everything you said. That was really wonderful. Thank you for sharing all of that information with us. Unfortunately, we are 1 minute over time, so we don't have any time to answer questions, but hopefully Steve answered some of your questions during his presentation.